of probability are going to be called nodal surfaces or nodes. And the number of nodes increases as n increases, and the number of nodes on an s orbital is given by n minus 1. So as we're going from n equals 1 to n equals 2, right, we said that was higher energy. Higher energy is always going to mean more nodes. So if you look at our radial distribution for hydrogen, 1s, 2s, and 3s orbitals, as we saw before, we had this 1s orbital with a nice little exponential decay, right? And then you have a node right at the surface of at the nuclear surface. If you look at a 2s, right? So there's our distribution, right? We're going to then square that wave function, and we're going to end up with one node in the middle. So it's going to be a radial node. So it's going to be like a sphere within a sphere. And for our 3s orbital, we're going to have a sphere and a sphere and a sphere. So we're going to have 1, 2 nodes. As the n number goes up, the number of nodes increases. Something similar happens when we change the L value. So remember, the L value is related to the shape, right? So our p orbitals are going to be kind of peanut shaped. They're not spherical like s orbitals. They've got 2 lobes, and they're separated by a node at the nucleus. So if you look at our kind of a top-down view of our probability distribution for a p orbital, it's going to have a lobe shape here and a lobe shape here, and those p orbitals are going to be the next level up, and they've got this kind of radial node, or this node, right, this planar node here in between. Right? And we're going to have 3 different p orbitals. We're going to have a px, which is along the x-axis, a py, which is along the y-axis, and you guessed it, a pz, which is along the z-axis. So we've got 1, 2, 3 p's. Each one is going to have a different orientation. If we look at our d orbitals, the first level is going to be that we're going to see them at is n equals 3. And they're going to possess 2 fundamental shapes. We're going to have an x, y, and z looking guy, and then our x squared, y squared guy as kind of the same shape. And then we're going to have the dz squared. So our xy, yz, xy, and x squared, y squared, they're going to have 4 lobes, and they're going to kind of look like a double dumbbell shape. Our dz is going to be a unique shape with a donut in the middle. Right? And I do like it because I like some donuts. Right? So that's what these guys look like. So our dxz is going to have orientation along, going to have some component up on this z-axis and along the x-axis. So it's going to be oriented along the x and the z-axes. The y and z is going to be along y and z. X and y is going to be along the xy plane. And the the x squared minus y squared is going to be on axis for x and y. And then our d squared is going to look like a p orbital with a donut around it. So the boundary surfaces for all 5 of the 3D orbitals, and it's going to show this with the signs indicated. So we will talk about what these signs on these lobes mean. Sometimes we'll see that represented as different colors a little bit later. That's going to come in for when we're going to start hooking molecules together. F orbitals and degenerates. The first F orbitals are going to occur at n equals 4. These orbitals are not really involved in bonding with compounds. All orbitals with the same value of n have the same energy value, and they're said to be degenerate. So degenerate just means they've got the same energy. In the ground state, the single hydrogen electron can be found in the 1s orbital, and this electron can be excited into higher energy orbitals. This is how we know that there are things like f orbitals and g orbitals. Right? We can take that electron from n equals 1 and give it some energy and promote it to n equals 6 and into a g orbital. Right? So we can kind of do that experiment. Right? This is a representation of what those f orbitals look like. I will not expect you to be able to draw these. But what you can see is that now that you've gone up to the next level, you notice that each time you go from a sphere to one planar node, so you go from a sphere to 2 lobes, and then you go from 2 lobes to 4 lobes. Now you're going to 8 lobes on your f orbitals. Right? They're going to be oriented along the axes or along the planes, and then you have this thing that kind of looks like that dz squared orbital from the D, but it's kind of got a double end to it. I do not expect you to know how to draw these. So, but I do expect you to know how to draw the D, the S, and the P's, right? Because you should be able to draw a sphere, a peanut, and a double dumbbell. So the coloration that you will sometimes see represents the positive and negative values of the wave function. When we look at the probability distribution, it's the square, and so it's always positive. So if we're looking at this, kind of distribution here, right, the probability has to, you can't have a negative probability of finding that electron. So the positive and negative lobes, which we'll sometimes see as like pink and blue, become important when we start talking about bonding. So that's why they're sometimes called pink and sometimes positive and negative, or it's pink and blue, or red and yellow, or plus or minus on there. And that's not saying that the electron is positive in that spot. It's just referring to what the wave function would be like. So the wave function itself would have a negative component, but yeah, there's equal probability of finding an electron in the blue spot as in the pink spot, and the electron's not negative here and positive here or something like that, right? But those will come in handy when we're talking about bonding. Next, we got the electron spin. That's going to be called ms. It can be either plus 1/2 or minus 1/2. It means the electron can spin in either of two opposite directions. And the Pauli exclusion principle says that in a given atom, no two electrons can have the same 4 sets of quantum numbers, so that if you're in that orbital, one of you has got to be spin up and one of you has got to be spin down. An orbital can only hold 2 electrons, and they're going to have opposite spins. Right, so what does this electron spin mean? Well, if you're taking this electron and it is spinning around, it's going to act like a charge that's rotating. It's going to induce a magnetic field. So you've got some sort of external magnet, and your electron will align in the presence of that magnet, or it will spin in the opposite direction in the presence of that magnetic field. If you have ever had an MRI, this is what is happening inside your body on the subatomic level, is that you are starting to align electron spins in that very, very high magnet. And then you're looking for the signal that's produced as those electrons then relax into a more random state. Spinning in one direction, the electron produces a magnetic field, that's Gemini A. Spinning in the opposite direction, because the magnetic field in the opposite orientation is shown in B. And they will never, ever, as this picture shows, be straight up. And the reason why they're never going to be straight up is because of the Heisenberg uncertainty principle. And so you're always going to have like this little precession in here where it's not going to be exactly straight up. Right? So how do we know this is happening? This is coming from something called the Stern-Gerlach experiment, where you've got an oven which produces an atom beam, and you've got a strong magnet, and you can have an electron spin, and they can go one of two ways, either spin up or spin down. So it's going to deflect either towards or away from that magnet. Right. So section 2.9, polyelectronic atoms. Are those atoms with more than one electron? So if you think about an electron correlation problem, since the electron pathways are unknown, electron repulsions cannot be accurately calculated. When electrons are placed in a particular quantum level, the orbital levels vary in energy as follows, where n is less than p, which is less than d, which is less than f. And so electrons want to go to the lowest n level first, and then within an n level, they will selectively fill s first, then p, then d, then f. There's something called the penetration effect. So a 2s orbital penetrates through the nucleus more than one in the 2p orbital. This causes an electron in a 2s orbital to be attracted to the nucleus more strongly than an electron in the 2p orbital. The 2s orbital is lower in energy than the 2p orbitals in a polyelectronic atom. The same occurrence can be noticed at other quantum levels. And so if we look at this penetration effect, where you've got an S in red here, it's getting a lot more of its electron density closer to the nucleus, and then P's got some, but it's intermediate, and D doesn't have very much near that nuclear center at all.